Hi, everyone. I'm Larry Lapidus. I'm also with Imperas, and I'm hopefully going to provide a little bit more depth on the DV side here with RISC-V. So let me start sharing my screen here. There we go. And get this into presentation mode. So let's talk about DV methodology. A few words about Imperas, although Kevin's already gone through a bit. RISC-V, design verification issues, the levels of DV methodology, and then actually drop into some of the key technologies here with the reference models and the verification IP, and then summarize. Let's talk about Imperas. So I think Kevin said, yeah, we're 14 plus years old and all that good stuff. Our background is in design automation, in FPGA and processor IP companies. So in truth, this is a bit interesting, a bit back to the future for some of us. For Simon Davidman, our founder, CEO, Simon was one of the co-founders of Co-Design Automation, and so bears some level of responsibility for System Verilog. For my part, I was part of Vericity. I ran worldwide sales at Vericity from about 2000 to 2004, and actually Vericity, and in fact, the FAE team that was my responsibility, crafted the first e-reuse methodology, and ERM over the last 21 years or so has evolved into UVM. So a long time ago, we were responsible, Simon, myself, Larry, were responsible for System Verilog and UVM, and then we went into Imperas, started doing tools and methodology for software debug, test, and analysis. Started applying this methodology to software because we believe that the embedded community is evolving so that no embedded system is going to be shipped without significant simulation-based verification. We've got some differences in how we're architected, but now with the introduction and adoption of RISC-V, we've added DV technology and methodology to the portfolio. So a bit of back to the future for Simon and Larry. Some history here with RISC-V. It was DAC of 2016. We first learned about RISC-V. It looked academic and fragmented. We sat through a tutorial there and didn't look good. But then 6 months later, at the RISC-V workshop at Google in Silicon Valley, there were 350 attendees from some very serious companies, and the instruction set architecture, the ISA, looks to be converging. So a couple months later, we joined the RISC-V Foundation. We built our first RISC-V processor model. We started participating in the compliance working group. And as part of that, we built and donated an instruction set simulator and tests. We started a year later in 2018. We introduced a methodology for not only adding but optimizing custom instructions for RISC-V cores. And then a few months later, we had our first paying customer using our RISC-V models, both for software development and for design verification. Early 2019 was the first tape out of a RISC-V based SoC using the Imperas model as the DV reference model. And then we started collaborating with Google on the DV flows using the open source instruction stream generator that Google had started building. In 2020, we started working with the Open Hardware Group and individual members of the Open Hardware Group on DV of the open hardware Core 5 cores. A year ago now, we presented 2 papers on RISC-V processor DB at DVCon Silicon Valley, one with open hardware, one with NVIDIA networking. That was actually a year ago. That was an interesting one. The 2020 DVCon actually was the last time I was with people before lockdown. And then Q4 of last year, just before the RISC-V summit, Imperas introduced the Imperas DV RISC-V verification product line. And I think Kevin mentioned a couple of new announcements that we made this week. In terms of customers and partners, there's a long list of users, partners, Nagravision, NVIDIA networking. I mentioned the paper we co-wrote last year. Micro, Silicon Labs, Dolphin Design, NXP, down the list here. NSI Texi is an interesting one because they're using RISC-V in an automotive application. And then partners, including RISC-V International, Open Hardware, Google, and Valtrix, and then processor IP vendors as well. And what we're seeing here is that the most complex RISC-V processor projects are using Imperas because Kevin showed we have support for the full range of the specification, and we have the capability of supporting custom instructions. So yes, we can do the simple RP32 IMC microcontroller, but we can also handle things that are 64-bit, that are application processor, that are multiple heart, multi-core, that have vectors, that have DSP, that have hypervisors, all sorts of things in there as we see the more complex processors. So why RISC-V? So it's an open standard, began in 2010 at the University of California, Berkeley. If you look close, you might actually see some Berkeley memorabilia on my wall back there. But that was actually a long time before 2010. Unlike most other ISAs, RISC-V is provided under open source licenses that do not require fees to use. This is just the architecture, not the processor implementation. Unlike other academic designs typically optimized only for simplicity, the designers, the original developers, intended that the RISC-V instruction set be usable for practical computers, practical applications. And so this is a comprehensive RISC architecture, reduced instruction set architecture. Also allows for users to add custom features. The key thing here is that freedom. It's the freedom and not the free. This is why RISC-V usage is growing so fast. That freedom enables domain-specific processing. RISC-V is growing in market segments where x86 and ARM are not dominant. This can be small microcontrollers for SoC management, replacing proprietary cores, doing things, for example, like power management, or you might see the RISC-V cores on NVIDIA or Imagination GPU arrays, where they're actually managing the array of other processors. We're also seeing RISC-V in verticals such as IoT and artificial intelligence and machine learning. This is a greenfield. Both of these areas are essentially greenfield vertical markets, and RISC-V, without some of the legacy features that are built into other instruction set architectures, can actually provide not only performance improvements there, but also reduced power and reduced area. So full PPA advantages in some of these new vertical markets. But also, we're seeing RISC-V in horizontal markets that cut across these verticals. And security is probably the big one there, because security is needed across the board in these verticals. And RISC-V with the open architecture is actually ideal for security. The freedom of this open ISA enables users to develop differentiated domain-specific processors. So RISC-V users include the traditional semiconductor companies, but also include embedded systems companies now practicing a vertical integration by developing their own SoCs. So what about DV issues? I'll actually be very quick about this. It's really due to all the freedom that you have, the feature selection, the design choices. So experienced processor teams know the costs associated with every feature. So every addition dramatically compounds the verification complexity. The cost of even a simple added feature can be huge and unknown to inexperienced teams. So what we're seeing is additional schedule, resource, and quality costs. We're seeing big risks. So you need to do DV. As of 2021, there are no off-the-shelf toolkits or products available. There are in-house proprietary solutions, but again, building your own processor adds schedule, resources, costs, risks, and DV we know is a significant cost already. This is going to increase it. So yes, you can acquire a RISC-V processor implementation for free. There are a number of open source ones. However, that doesn't mean that using it is necessarily going to be free. There's going to be DV costs involved here. Okay, sorry, moving on. Let's talk about the 5 levels. Kevin talked about this briefly, but I just want to go into a couple of these. The first is the 3rd level, the post-simulation trace log file compare. We think of this really as entry-level DV. Yes, there's Hello World and some self-tests that are available here, but really the trace log file compare is the base minimum that someone would use for a DV of a RISC-V processor. So here you're using a random generator to create the tests. You're writing a trace log file from the simulation of the reference model, the ISS. You're writing a trace log file from the RTL simulation, and then doing a comparison. What we've done here, working with Google, Chips Alliance, Low Risk, is use the free instruction set simulator, RISC-V OVP Sim Plus. It includes trace, includes a GDB interface. And as I said, that's available for free. There's a link for it there. And then on the instruction stream generator, using RISC-V DV from Google Cloud and Chips Alliance. So that's the entry level. And then there's the 5th level, the highest quality DV methodology, an asynchronous step and compare methodology. The diagram here shows this for the open hardware flow for the CV32E40P core from Open Hardware. So design features needing this asynchronous step and compare methodology include an out-of-order or multi-issue pipeline, multi-ARC processor, debug mode, interrupts, asynchronous events. There are some key components here, such as the tracer that goes with the RTL, the step and compare modules that are actually doing the control work in the test bench. There's interrupt assert, debug assert. This can be hard and complex and expensive to get working. And the challenge is extracting the asynchronous information from the microarchitecture of the RTL pipeline. That can be challenging sort of thing. Here's another example of this. This is NVIDIA networking step and compare flow. This is from the DVCon paper that we presented last year jointly, NVIDIA networking and Imperas. So this is completely different here. We see, well, the one similarity, the Google UVM instruction stream generator, and then taking this and running it through a compiler. This was processor they were working on was actually multi-art processor, and so you see things are done on a per heart basis here. And then running the RISC-V instruction set simulator, and then running the results into a comparator. Here, actually, they've got SpecMan running here, and so the test environment was SpecMan, and actually everything was encapsulated there using C interface to the Imperas model. They've got the RTL running here. Comparison was done, and actually, again, this is an asynchronous flow, so at any failure, they're able to stop the simulation and go and do debug. So this was Imperas simulator, Cadence Excellium for the simulator. Everything is stepped in parallel, enables both asynchronous and synchronous events. And actually, one of the interesting features here is that there's an interactive co-debug capability, so that using the Imperas debug environment and the Cadence debug environment together, you can synchronously stop the two simulations, the reference model and the RTL, and that makes for a very powerful debug environment. So asynchronous step and compare. Instruction by instruction lockstep compare, including asynchronous events. That's what we're talking about here. This is the highest level of processor DV for RISC-V. It allows for immediate comparisons, debug introspection at the point of failure, and doesn't waste execution cycles after the failure. Focus on the asynchronous events, the control flow, hardware real-time events, supports multi-heart processors and out of order. It can be hard to develop and set up. Really depends on the RTL tracer features and an understanding of the pipeline. Can be expensive in terms of time, resources, and licenses, so it can cost a lot per bug found, but bugs are even more expensive if not found early enough. So it's the most comprehensive, most efficient DV approach. But going back to that expensive piece of it, expensive in time, resources, licenses, the next steps for asynchronous step and compare then are standards for the test bench and building verification IP. Because if we can make this easier to use, quicker to get up and running, then it's going to be a lot more valuable to people. So let's go take a look at those things. So some of the key technologies here with the asynchronous step and compare are the reference models then and the verification IP. This is a block diagram of the DV environment, the processor DV environment. There are 5 key components: functional coverage, the tests themselves, the device under test subsystem, which can include some verification IP in here for interrupt generation, for example, the test bench itself, which could be system Verilog C, C++, and the reference model subsystem, which includes the reference model itself, as well as various DV functionality. So these are some of the key DV technologies, but there's also this RVVI DV standard that we'll talk about actually in the next slide. So RBVI is the RISC-V verification interface standard for connecting to the test harness. We announced this earlier this week. It's available on GitHub as a public open standard. There are a couple of components that are available right now. There's more that's being added on to this. There are some Verilog device under test interfaces that handle the tracer data coming from the device under test subsystem, and then APIs for working with the reference model subsystem. And again, this supports System Verilog C, C++ test benches. So working with standards always make things easier, and developing standards for verification, specifically RISC-V processor verification, is going to make it easier for people to build their own, add custom instructions, take advantage of the freedoms that RISC-V provides. In the device under test, the RTL, not too much to say about this, except this bit here. The quality of the tracer determines the potential capabilities of the DV environment. So the tracer is going to be that module, usually built in the RTL, that's going to allow introspection into the RTL, that's going to pull data out, and the different pieces of data that it pulls out is going to be the limiting factor for the DV environment. Third piece here is the RISC-V reference model. So if we're looking at reference model, actually we want to build something that is not just for verification, but also useful for software development. We want to use the same model for both. It's got to model the ISA, including all versions of the ratified spec and the stable unratified extensions, easily update and configure for the next project. User extendable, model actual processor IP if you're using that. Well-defined test process for the model, not just for the RTL, but for the model itself. It's got to interface with other simulators, interface to software debug tools, interface to software analysis tools, interface to architecture exploration tools. Most RISC-V instruction set simulators can be at most a couple of these environments. But actually, Imperas, we've been building models and simulators well before RISC-V. Our technology was built to satisfy these requirements, matured through usage on non-RISC-V ISAs over the last 12 plus years. So in RISC-V, we've got a big library. We're supporting the full specification. We have models of processor IP vendors. We also provide custom models for users building their own cores. It's easy to add custom instructions. I'll actually go into that in just a minute. But a key thing here is that these models are built using a test-driven development methodology. Tests are built at the same time features are added. We use a continuous integration flow, so our developers have to check in code as they add features. They have to test as they check in code. We've got well over 15,000 tests, and there's additional testing by the processor IP vendors to validate the models. Kevin showed this slide where we've got the reference model. We've also got model configuration. So there are over 150 different parameters to modify the Imperas reference model. And that's just within the RISC-V specification. And then this model and config file run with the Imperas simulator. When we add custom instructions, when we or a user add custom instructions, it's just an extension file that goes with these other files. And actually, every one of the Imperas tools is going to work with this. But the nice thing about doing this is that every Imperas user is using this RISC-V base model. And so this gets really well tested, really well used. And then anything new is just in this piece of it. So this is in the reference model, the only place that bugs are going to be. In terms of adding custom instructions, I'm going to go through this just briefly here. The key thing in RISC-V is that typically you're not trying to optimize a pipeline, you're trying to optimize the performance of a specific C application or a domain of applications, a set of applications. And so you're going to want to start by characterizing that application using simulation, using tools like trace and debug, using function profiling, for example. And then you can go and simulate that in the instruction-accurate simulation environment that Imperas provides. We're running over 1 billion instructions per second on a standard PC. We're doing function profiling. And in terms of this example, and actually this is a real example, we're adding SHA-20 encryption instructions to RISC-V. We see that this particular function, the process line function, is taking 21% of the execution time, and we'd like to reduce that. To do that, we're going to develop new custom instructions, add those to the application, to the model. If we add those just to the application, so we've added these SHA-20 instructions to the application, but when we simulate, we get an unimplemented instruction exception because we haven't added the instructions to the model. So we go and do that, and we resimulate. And actually, what we're seeing is that the instruction count has been reduced. The simulation time has actually been reduced. That's pretty cool. We're able to use the trace tools here. That works. We're able to do debug in the Imperas environment. Our multiprocessor debugger, it's an Eclipse-based tool that can be used here. And if we go back to the function profiling, we see that this process line function that was 21% of the execution time is now under 15% of the execution time. So we're going to iterate on that, optimize and document the model, and then deploy the model. Pretty straightforward flow. There are actually tutorials on how to do this in the Imperas environment. Then in terms of RISC-V verification IP, the verification IP is needed for ease of use, for scalability, for extendability, for performance, and for debug. So again, you want standards, you want verification IP. This is going to make it easier to use. Schedule reduction is the other big thing. The DV functions include selecting which model, which variant, configuring the model, the reference model encapsulation. There's an instruction coverage capability in Imperas. There's storage, state storage for the DUT. There's the synchronization technology, comparison technology. And the idea is that this is simple to use. You just configure this verification IP, and it can be used with your test bench. Seeing this in action, so here we've got the device under test, here we've got the test bench, here we've got the verification IP, this Imperas DV piece of it. We see that the communication between the test bench and the Imperas DV piece of it, including the reference model, is done using these RVVI APIs. So that's a key piece, using the standards. Now we're also using the verification IP. Again, doing the model setup, doing the configuration, selecting the capabilities, synchronous or asynchronous, step and compare, using the instruction coverage, and this just works. To summarize, the RISC-V processor developers need to do comprehensive verification of the RTL implementation. That's because you're building a new processor. It's something that's got to be done here. The processor DV methodology has been evolved by Imperas together with customers and partners. You saw that list of customers and partners, pretty extensive there. The asynchronous step and compare methodology provides the most comprehensive, but also the most efficient RISC-V DV flow. And key technologies include the Imperas Open Virtual Platforms Reference Model and the Imperas DV verification IP. I'd like to thank you all for spending some of your afternoon with us today. My name is Larry Lapidus, Larry L at Imperas.com. I'd be happy if you send me any questions. But at this point in time, I think we're going to go ahead and end this. We're probably all getting this message that the session will end in 1 minute. I hope you enjoy DVCon. Hope that when I see you in person, it'll be not in the too distant future, maybe at the Design Automation Conference in July this year. Have a good day, everyone. Bye now.